In the previous lesson, what we did was to work with an arithmetic mean, and notice that the name of today's lesson has to do with a geometric mean. All right? So let's look at an example, and I think that this will illustrate this idea. Here we have a problem in which it says find two geometric means between 3 and 192. All right? So let's set the problem up as we have before, in which our first element is 3. We then are looking for some element which we would like to insert in that slot, and then another element here, and then in fact our fourth element is the number, what? 192. And what is our formula that has to do with a geometric sequence, Doug?
A to the n.
A sub n.
A sub n is equal to a sub 1 times, it would be n. What?
Does anyone remember what it is?
That's right,
R. Okay, we use the
R to the
letter
n
R
minus 1.
raised to the n minus 1 power. Okay, now let's see. Here we have the element 192 is what term? This is the fourth term, is that right? Is equal to a sub 1, which is 3 times r raised to the 4 minus 1, or to the third power. And looking at this, we have r cubed then is equal to, and if we divide 3 into 192, we get a number which is what? 64. And now notice here we have a cubic equation, a polynomial equation of degree 3, in which we want a number which when multiplied by itself 3 times is equal to 64. And I think you will all agree that there is exactly one number which will do this. And what is that number, Bill?
4.
It's equal to 4. And now notice here then, r is equal to 4, where r is our common ratio. So then coming back here with respect to our geometric sequence, the second term is going to be what number?
12.
It's going to be 12, and then the third term is going to be 48. And our two geometric means between 3 and 192 are 12 and 48. All right? It's the same concept as we had earlier, but it's with respect to a geometric sequence. Let's look at another example, and I think that this is going to generate a theorem which we would like to talk about. And let's see what this problem looks like. It says, what is the first term of a geometric sequence whose second term is 64 and whose sixth term is 4? Okay? So we now are looking for that first term. The second term is 64. There must be some third term which we're not particularly interested in, a fourth term, a fifth term, and then the sixth term is what number?
4.
In this case, 4. Okay? Again, let's set up our pattern of a sub n then is equal to a sub 1 times r to the n minus 1 power. Now let's then substitute this number 4 for a sub n. So here we then have 4 then is equal to, now a sub 1 we do not know. That's the number that we're looking for. And in fact, we also do not know r. But in terms of n minus 1, what number is n in this case? With respect to the last term, it's 6. So 6 minus 1 then is 5. Now notice here in this one equation we have two variables. Well, in fact, we have some other information given to us, namely that the second term is 64. So let's see if that won't help us. Making the same substitution, 64 then is equal to a sub 1, which we do not know, times r raised to what power? It's going to be 2 minus 1, which is simply to the first power. Let's look now here at these two equations, and let's look for a name for, say, a sub 1 right here, in which it will be equal to what? 64 divided by, in this equation, Brenda, 64 divided by r. And now let's make that substitution. There's a name for a sub 1 in this equation right here. I think then we can find the number r, and from r then I think we can find a sub 1, okay? And right here we then have r to the 5th divided by r is another name for r to the 4th. So we have 4 then is equal to 64 r to the 4th power. And turning this equation around and solving for r to the 4th power, we have r to the 4th is what? 4 divided by 64. 4 will divide both 4 and 64, and we have what? 1 over 16. Now, notice here we have a 4th degree polynomial equation. R to the 4th power is equal to 1/16. And notice here that this number 4 is an even number, and therefore, what numbers numbers will make this sentence true? R to the 4th equals 1/16. And Tom, what can we say? R then is equal to 1/2. Is there any other number there, Doug?
Negative 1/2.
or r is equal to a negative 1/2 will make this sentence true. Now, if r is equal to positive 1/2, then a sub 1 is going to be equal to what number? Now let's come back here and look at our original sequence in which our second term is 64. So some number times 1/2 must be 64, and Don says
128.
the number r, a sub 1 rather, must be 128, a positive 128. And in fact, if r were equal to negative 1/2,
then a sub 1 is equal to what number can we have here, Bill?
Negative 1.
a negative 128. Now notice in the second case here, in fact, if we were to come back to our original sequence,
If this were a negative 1/2,
that is, if the ratio r were negative 1/2, in which our first term is a negative 128, this is negative, positive, negative, positive, negative, positive. And in fact, I think you would agree that both of these numbers will make this sentence true, or
certainly our conditions of the problem
would be satisfied, and we have these two values. Now, the reason I use these two examples is to illustrate this idea of these polynomial equations of different degrees. And notice here we have r to the fourth power is equal to 1/16, and we have a fourth degree, a power, which is an even number there. In our first example, we have r cubed is equal to 64. It's a third degree. It's a odd power equation in which we ended up with just one number, which will make this sentence true. So let's try to generalize this, and what I'd like to do is to write this in the form of a theorem. We're not going to prove it, because in fact the proof is beyond what we can do right now. It requires this completeness axiom, which we're going to do in a few days. But let's see how we may state this theorem. Well, in fact, I'd like to break it up into two parts, in which, well, let me say, if n is an odd, let me underline the word odd, positive integer, okay? We're talking about an equation of a pattern, well, let's call it r to the nth power is equal to, let me just call it some number a here. Then this thing has how many roots? Has exactly, right? Exactly, what can we say? Exactly one real root, okay? Real root. Now, notice here, if n is an odd number here, r to the nth power is equal to a, has exactly one real root. And I think that this is something that you remember from your work in your first year algebra course. Now, there's a second part of the theorem in which if n is an even positive integer, let's see what we may say about that. Then, let me include it over here, then, let's see now, the same equation, r to the nth power is equal to a, has, and in fact here I think we can break this up into a few parts, has, now it will have exactly one, again, exactly one root if, now let's say something about the number a. What kind of number must a be in order to guarantee it's just one? Well, roots. If, now what can we say about the condition a? What kind of a number will a be? Now notice here, n is an even positive integer, and looking back here, for example, right here we have r to the fourth power is equal to 1/16. It's an even positive integer, and that gave us how many roots then to that equation? And Tom? It gave us two real roots, but what kind of number then is a? In this case, a was what value? In this problem right here, a was what number? 1/16, is that right? Which is what kind of a number, certainly. Bill?
A positive number.
A positive number. So I think if a is greater than 0, then in fact we're going to end up with two real roots. Okay? And then finally, if you remember from what we did in our Algebra 1 work, if our number a were a negative number, then what is our conclusion about something, an even power of that? R to the nth power is equal to a, where a is a negative number. R squared equals -3, for example. Is there any number r in the set of real numbers which will make that true, Michael? Then, in fact, in that case, we would have no real root if a were less than 0. Okay? So we have these two different parts to this theorem, one of which is if n is an odd positive integer, then in fact we will always have one real root, exactly one real root. And the only problem arises is when we have an even positive integer for that exponent, and then you have to consider what it's equal to. And of course, if it's equal to 0, there is just one, namely the number 0. If it's greater than 0, that's the case in which you're then going to have 2. In fact, they will always be one positive and one negative of each other. They'll be opposites of each other. And then if a were less than 0, we have no real root in the set of real numbers. Notice again, in the set of real numbers. Well, let's look at another example. And here we have a problem which says find the geometric mean of 12 and 27. Again, it has something to do with the similar idea as we did with respect to an arithmetic mean. Let's set it up in which we are now looking for one number here. And let's see how we may do this. A sub n then is equal to a sub 1 times r to the n minus 1. Let's do this two different ways. The first way is the same system, the same method that we were just using in examples 1 and 2 over there. And here we have what? 27 is equal to, and who would like to make this substitution here? And Dick?
12 times
12 times
r to the 3 minus 1 or second power.
r squared. Okay, now notice here we have r squared then is equal to 27 over 12. Is that right? Which in fact, let's see, 3 will divide. Is that right? So this then is equal to 9/4. Now again, notice that we have r squared is equal to 9/4. And our theorem that we have just said is that if this is an even positive integer, and if this number is positive here, then in fact how many roots are going to make this sentence true? How many numbers will make it true, Doug?
Two.
2 numbers. And what then are those 2 numbers? Therefore r is equal to, 3/2, Peter says, or r is equal to negative 3/2. Now, if r then is equal to a positive 3/2, looking here we have 12. Well, what then is this number that we have here? It then would be the number 18, and then we have 3/2 times 18, I think you will agree, is 27. Now, there's an agreement that I think we should make. Now, notice here that we started with these 2 positive numbers, 12 and 27. So let's make an agreement that if we have 2 positive numbers in which we then are asking for the geometric mean, let's then agree that we will take the positive one as the geometric mean, okay? If the 2 numbers here were negative to begin with, then we will agree to take which one as the geometric mean? Bill, let's then agree to take the negative one. So that in this case, the number negative 3/2 for the value of r then, by our agreement, will not give us the geometric mean, okay? Now, the reason I selected this problem is because there's a definition of a geometric mean, of the geometric mean, that I think that you are familiar with, certainly, one that you've seen before, in which suppose I had 2 numbers a and b. That number m, which I am writing in terms of this proportion, is given a special name, and in fact, does anybody remember there were 2 different names that we gave it? One of them was geometric mean, but there was another one that perhaps some of you will remember, and does anybody have any recollection of that? Don? The mean proportional. The mean proportional. P-R-O-P-O-R-T-I-O-N-A-L. The mean proportional, in which we have, if you remember, we call these 2 numbers the means, and we call these 2 numbers the extremes. And in fact, there was another relationship that you learned, more so in words, but we could do it in terms of our algebra, and it had something to do with the product of the what? Does anyone happen to remember that? The product of the means is equal to the product of the extremes. In this case, we'll have m squared then is equal to a times b. Now notice here again, we have that number, which is the mean, squared is equal to the product of the 2 given numbers. So therefore, in terms of the numbers that we have in this problem, a happens to be 12, b happens to be 27. We have 12 times 27. Now let's then look for this number. In fact, I think I'd like to rewrite this in a slightly different pattern. 12 I may write as 4 times 3, and then 3 times 27 is what number? 3 times 27 is 81. So there we have m squared is equal to 4 times 81. Therefore, m is equal to what number? 2 times 9. Let's just indicate that. Or m is equal to 18 in this case, but then remember now here we have m squared is equal to 4 times 81, and our theorem tells us there's another number which will satisfy that. So let me just write that as what? Negative 2 times 9. Is that right? And in fact, we would rather give this a name of what? M then is equal to 18, or M then is equal to negative 18. But again, our agreement that we made earlier was that if A and B are both positive, then the geometric mean we will take to be which one of these two? And we will take the positive one. So with respect to this particular problem, let me just... Number 21, in which I'll ask you to study.